Chapter 9, Section 9, Practical Applications, Normed Space and Inner Product Space. Normed space and inner product space are not just abstract mathematics. They play important roles in how we build, train, and optimize machine learning models. In this section, we will explore how norms help measure model complexity and how inner products enable us to align features and weights. Through the lens of regularization techniques like lasso and rate regression, we will see how these mathematical structures support better generalization and model performance in real-world data science problems. First, let's recap the fundamental concepts: normed space and inner product space. A normed space is a space where we can measure the length or size of a vector. We have a way to say this vector is longer than that one. An inner product space is a richer structure where we can not only measure length but also angles between vectors. We can say these two vectors are pointing in the same direction, or they are perpendicular. This basic ability to measure size and direction is the mathematical foundation of many operations in data science. In this section, we will see how these mathematical tools help us solve a real and practical problem in machine learning, the problem of overfitting. Overfitting is the phenomenon where a machine learning model fits the training data too closely, capturing noise and random fluctuations rather than the true underlying patterns. This impairs the model's generalizability and leads to poor performance on new, unseen data. Regularization is a set of techniques that we use to prevent overfitting. It is like adding a smart rule to our learning process that says, don't chase every small detail, focus on big general patterns. And here's the important connection. Regularization works by using the idea of norms and inner products to control and adjust the model's behavior. Now, imagine you are training a model. Training a model fundamentally means finding the optimal parameter values. In linear regression, the parameters are the weights that determine the relationship between the independent variables and the dependent variable. In model training, we want the model's parameters to find a balance between fitting the training data well and not becoming too extreme or wild. Fitting the training data well means achieving small error, while not becoming too extreme or wild means achieving small model complexity. But how do you measure if the weights are getting too big? The norm of the weight vector tells you how large are the parameters overall. If the weights become huge, it usually means the model is trying to fit every tiny noise in the data, overfitting. So, keeping the weights small is one way to make your model simpler, more stable, and better at generalizing the new data. Next, let's dive into the concept of regularization. Regularization is a method to prevent overfitting. It works by adding a penalty to the model's loss function based on the size of the weights. The penalty is calculated using a norm, either L1 or N2. In practical terms, if we use the L1 norm to penalize large weights, we are applying L1 regularization, which is used in lasso regression. If we use the L2 norm to penalize large weights, we are applying L2 regularization, which is used in rate regression. We are literally using the math of normed spaces to guide the model toward better, more reliable solutions. Let's now look carefully at two major types of regularization, L1 and L2. L1 regularization is also called lasso. In L1 regularization, the penalty is based on the L1 norm, the sum of the absolute value of the model's weights. Mathematically, the new loss function is defined in this way. Here, lambda is a parameter that controls how strong the penalty is. The L1 penalty encourages many weights to become exactly zero. As a result, the model automatically selects important features and ignores the rest. If you have a lot of input features, but you believe only a few of them are truly important, L1 regularization helps you build a simpler, more interpretable model. Next, let's talk about L2 regularization, also called ridge. In L2 regularization, the penalty is based on the square of the L2 norm, the sum of the squares of the weights. Mathematically, the new loss function is defined in this way. The L2 penalty shrinks the weights towards zero, but really forces them exactly to zero. All features are still used, but their effects are reduced. If you believe that many features have small but real effects, L2 regularization helps you control the influence of any one feature without throwing it away. So, why does regularization matter in data science? If you are working with high-dimensional data, like text data, genomic data, or any situation with thousands of features, L1 regularization is often very useful because it selects important features automatically. If you are working with low-dimensional noisy data, where all inputs might matter a little bit, L2 regularization is often better because it shrinks and stabilizes the model without discarding the information. Thus, the choice between L1 and L2 is not arbitrary. It reflects the structure of our problem and prior belief about the data. So far, we have seen how normed spaces, and particularly L1 and L2 norms, directly shape the behavior of machine learning models through regularization. In the following, we will step further into the structure. We will see how inner product spaces relates to regularization of a linear regression model. Let's recap what an inner product space is. An inner product space is a vector space equipped with an inner product, which enables us to measure not only length of our vectors, but also angles and similarity between vectors. In simple terms, the inner product tells you how much two vectors point in the same direction. If two vectors are orthogonal, their inner product is zero, meaning they are completely unrelated in the space. In machine learning, we often face not just the problem of how big the weights are, but also how aligned they are with certain important directions. Let's break this down carefully. In linear regression, every predicted value is based on an inner product. Here, W is the weight vector, and Xi is the input feature vector for the ith data point. Each prediction is literally the degree of alignment between the model weights and the input features. Thus, if W and Xi point in the same direction, the predicted value will be large and positive. If they point in opposite directions, the predicted value will be negative. If they are orthogonal, the model predicts zero contribution. In sum, the inner product structure allows the model to match or align weights to features efficiently. Now, let's connect this to regularization. In L2 regularization, the penalty term can be written in this way. It is based on the L2 norm, which itself is defined via the inner product. Thus, L2 regularization is minimizing the self-inner product of the weight vector. It tries to keep the weight vector short, but more importantly, it preserves the inner product structure, allowing features to combine smoothly rather than sharply dropping some features to zero. In summary, lasso can work in a normed space. Lasso tries to keep the model small by minimizing the sum of absolute values of the weights, the L1 norm. It encourages sparsity. Some weights become exactly zero. For this, we only need to measure the size of vectors. So a normal space is enough. We do not need inner products or angles. In contrast, ridge needs an inner product space. Ridge shrinks all weights smoothly using the sum of squares, the L2 norm. The L2 norm is actually derived from an inner product. That means ridge regularization relies on geometry, size and direction. Therefore, it needs an inner product space to function properly. Let's wrap up. Simple regularization like lasso only needs vector size, so it works in a normal space. More structured regularization like ridge depends on the size and direction, so it requires an inner product space. And in modern machine learning, we usually care about both, so inner product spaces are essential. Thank you for watching. Please thumbs up and subscribe to my channel.